here to prove that a function is holomorphic on an analyst, then it has Laurent series. And we have this region. I cleaned this up so to give myself enough room so I might be able to finish. We basically have this picture here where we've got two circles, gamma 2 and gamma 1, and then we're going to add this little auxiliary piece that cancels each other out. And of any point in Z, pick any point in this analyst, and then just draw the orange piece far away from Z. Then what you get is you can unfold this, slice this up so that you get purple, orange, go the opposite way around the blue, and then go back to orange and then purple. You get a region, an enclosed region, which allows us to use Cauchy's integral formula, which boils down to, once you get rid of the oranges, integral once around the purple and once in the opposite direction around the orange, so you get gamma 2 minus gamma 1. And we're going to figure out what these are, and these are what's going to give us our Laurent series. And so I'm going to focus in on the integral around gamma 2. The integral around gamma 2. Now we're free to this picture. In this picture, I'm integrating around gamma 2, which means I'm going to take my w's, this is dw, so my w's look like this. In particular, my w's have a greater modulus than z. So, so what I have is 1 over w minus z. I'm just going to look at this portion of the integrand, only the denominator. This is going to be equal to, I can factor out a w, and I get 1 over 1 minus z over w. And in particular, in this picture, z is closer to the origin than w, whereas z over w, modulus has to be less than 1 because w is bigger. So 1 over w minus z is equal to the sum of 1 over w times z over w to the n, where n goes from 0 to infinity. Right. So this is what I have for delta, or for gamma 2. And I need the fact that we're using gamma 2 because w is farther away, and I'm using that fact to get convergence. And I can play the same game for gamma 1. To look at the integral for gamma 1, I get 1 over w minus z. Well, I have the opposite problem now. My w's here are closer than z, so I'm going to factor it out the other way. And maybe I'll factor out a 1 over z negative, and that's going to give me, if I factor out negative 1 over z out of this, I'm going to get 1. If I factor out negative 1 over z here, I get w over z. And where w over z modulus is less than 1, because look at the picture. W is closer to the origin than z. It has to be. So I get 1 over w minus z is equal to negative 1 over z times the sum from n equals 0 to infinity w over z to the n, which, if we want to write it as, with the z on top, we get negative 1 over z times n equals about negative 1 to negative infinity of z to the n over w to the n. In fact, let's just turn this. I'm losing myself. Wait 1 second. Okay, yeah, I got it. So this is exactly right. So this integral is equal to 1 over, or f of z, in other words, at this green point z is equal to this integral times f of w times, for gamma 2, the denominator ends up being just 1 over w times the sum from n equals 0 to infinity of z to the n over w to the n. dw minus 1 over 2 pi I times the integral, again, f of w times the integral of minus 1 over z times z to the n over w to the n. That's where I screwed up. This should be totally like that. So these negatives turn into positives. And if you do the algebra and do it correctly, which I'm not guaranteeing that I have been doing, this is equal to, I can use a theorem, by the way, to pull the sums outside. This is equal to the sum of 1 over 2 pi I f of w over w to the n plus 1 times z to the n. That's a power series, plus the integral from n equals negative 1 to negative infinity of 1 over 2 pi I integral